Okay, so we left off last class. We were talking about similar figures. Little things like, Jasper trying to avoid crushing his house with a tree and stuff like that. You want to try again? Is that what you're saying? Other things that we can use similar figures for. Let's say we want to know how tall a hill is or something like that, something that we can't get to measure. We can measure that height, again, using a similar figure. If we can somehow approximate the distance to a certain point, let's say we have a range finder and we can tell that the distance from this point down here to the top of the hill is 840 feet. We construct that line of sight, and similar to what we did before, we're going to have somebody who's 6 foot tall. Again, Jasper's dream world again, right? 6 foot. And we're going to line it up so the top of their head is in that line of sight to the top of the hill. And we're going to measure their distance. So we know they're 6 feet tall. The distance here, let's say that ends up being 42 feet from our spotting point there. How can we use that to find this height right here? H, the height of that hill. Perfect. We would need to find the length of the hypotenuse. What we need to do is we need to look at this triangle right here, the red one. We've got 6 feet here and 42 feet here. We need the length of the hypotenuse. Now, at this point, we've done this enough that we're not going to go through the whole formal procedure. There's a shortcut. It's just the square root of 6 squared plus 42 squared. Does that make sense? That's just a squared plus b squared equals c squared, but we're going to shorten it up. So second square root of 6 squared plus 42 squared. 42.426 feet. So now what? You could do it as a percentage, but let's just do it as similar figures. We have that 42.46. That is the corresponding side to the 840. So 42.46 426 corresponds to the 840 feet. Now I'm trying to find H. Is H going to go on top or bottom here? It goes on bottom because it's from the same figure as the 840. On top is going to be the 6 because that is the vertical dimension out of the other triangle. So then we will cross multiply and divide. So 840 times 6 divided by 42.46. 118.79, 118.80 feet. Oh, it's not really that steep. That's about, what does that come out to be, about a 12 or 13% grade? Yeah, I know. It's the distance from where we're at. The grade of the hill is a lot steeper, that's for sure. Okay, so we can use these similar figures for a lot of things. We have similar figures like this. Now, what do I need to know about these to know they're similar? Corresponding angles would help. Now, triangles, all I need to know is 2 angles. Figures like this, I would need to know a little bit more. But I'm going to give you those 2 angles, and I'm just going to tell you that those are similar, that one's an enlargement of the other. Now, let's give you some sides here. Let's say that this here is 9 inches. This is 6 inches. I'm going to call this X and Y. Over here, I'm going to call this 15. This I'm going to call Z. Oh, let's see here. I'm going to call this one 45. And let's see. And the bottom one here, got to come up with a good one for that. We call it 60. Screw that. Let's call it 56 inches. So we have those measurements. How do I find those missing dimensions, X, Y, and Z? In your notes, find them for me quick. So first thing we need to find is we need to find a set of corresponding sides that we know the number for both figures. Which side is that? Six and 15. So I can have 15 to 6 or 6 to 15. It doesn't matter which. I'm going to do the 15 to 6. So now if I'm going to find X, is X going to go on top or bottom? X goes on bottom because it's from the same figure as the 6. What goes above the X then? 45 is the corresponding side to the X because both of them are between the angle marked with 2 arcs and the unmarked angle. So 45 goes here. If we cross multiply and divide, we will get that X equals 18. Still got the 15 to 6. If we're looking for Y, Y is going to go on bottom. What's going to go above the Y? 56 goes above the Y. We will cross multiply and divide. 6 times 56 divided by 15 is 22.4 works for me. Does that look right? And finally, we still got 15 to 6. Looking for Z. Z is going to go on top because it is from the same figure as the 15. What goes below the Z? The 9. We cross multiply and divide there. We're going to get that Z equals, careful, 22.5. $15 times 9 divided by 6. Yeah, 22.5. Yeah. 15 goes to 6, right? Z goes to 9. So 15 times 9, then divide by 6. Does that make sense? Any questions? Okay. This does not have to just apply to two-dimensional figures. It can be three-dimensional figures. We can have something interesting like this. So something like this, or let's make this piece here 6 feet. We're going to call this here 10 feet. And this one down here we're going to call 20 feet. Screw that. We'll call that X feet. This one here we're going to call 15 feet. This we're going to call Y feet. And this we're going to call 50 feet. In your notes for me, find X and Y quick. See what you come up with. Okay, so here, where's our pair of sides that match up? 15 and 6 again. To find X, where's X going to go? Bottom. It's from the same figure as the 6. What goes above it? 50. We cross multiply and divide. 6 times 50 divided by 15 is 20. So X is 20 feet. We got the 15 over 6 again to find Y. Y is going to go It's from the same figure as the 15. It goes on top. Below it is 10. We cross multiply and divide. 15 times 10 is 150. Divided by 6 is 25. That's 25 feet. So what I have for you today, I'm going to have a quiz for you, and I'm going to have a new packet for you to work out of. Let me get those passed out for you. So you've got your packet there. You've got that ratio and proportion packet to work on. Our next step is we want to take this stuff. We looked at these three-dimensional shapes here, and those ratio of lengths still hold true. And that's what we've been looking at so far, is just a ratio of lengths. But there are other features of an object that are proportional. For example, let's take a rectangle. Let's say this is 2 inches by 5 inches. And I'm going to blow it up. So let's say this side becomes 6 inches. What's this side up here going to become? 15 inches. So we have a ratio of lengths here. That ratio of lengths is, 2 becomes 6 or 5 becomes 15, either way. And we're going to reduce it, both divided by 2, to get a 1 to 3 ratio of lengths. What is the area of this figure here? Yeah, 2 times 5 or 10 inches squared. How about the area of this figure? 6 times 15, 6 inches times 15 inches, or 90 inches squared, square inches. That ratio of areas is different. The ratio of areas, if I write it out, it's 10 inches squared to 90 inches squared, or reduces to a 1 to 9 ratio. They're not the same. Well, let's take a look at another figure and see if we can find a relationship here. So let's take a triangle here. Let's call this, we go 6 by 10. And we're going to blow that one up to be 12 by, what would this bottom dimension have to be? 20. So as we can see there, our ratio of lengths is 6 became 12 or 10 became 20. Either way, it reduces to a 1 to 2 ratio, or 1/2 ratio. Well, let's look at our ratio of areas. What's the area of this? Yeah, 6 by 10 divided by 2 is 30 inches squared. And this one? 120. Very good. 12 times 20 divided by 2 is 120 inches squared. That gives us a ratio of areas of 30 to 120. And both of those can be divided by 4 to reduce that to get a 1 to 4 ratio. There we go. To get from the ratio of lengths to the ratio of areas, we square it. To square a fraction, remember, you square the numerator. What's 1 squared? 1. And then we square the denominator. What's 2 squared? 4. So that gives us that 1/4. Same up here. We have a 1 to 3 ratio of lengths. 1 squared is 1. 3 squared is 9. Now, in figures like this, it's pretty simple to just find the area of the new figure. But if we have an unusual shape, something like that, for example. Come on. I'm cheating, so I don't have to try to redraw it. Get back here. So let's say we had this shape here where this dimension right here was 8 inches, but we needed to shrink it. We shrink it so that this dimension now is 5 inches. Before we shrunk it, though, before we reduced it, the area was 320 square inches. What's this new area going to be? Well, we can figure that out by going through that ratio of lengths. What's our ratio of lengths here? 5/8 or 8/5, either one. We'll go 5/8. Now then we can use that to find a ratio of areas. How do we find the ratio of areas from the ratio of lengths? We square it. Very good. 5 squared is 25. 8 squared, 64. Now, where does the 320 go? It's with the 8, and the 8's on bottom, so it goes on bottom. So to find that new area, we can cross multiply and divide. 25 times 320 divided by 64 is 125. This is 125 inches squared. Does that make sense? Okay, so in your notes, I want you to try to find this. Is it? It kind of does look like a rabbit, doesn't it? Okay, so this shape, this dimension right here, has been enlarged from 10 feet to 16 feet. Let's make it a little less obvious. Let's go from 10 feet to 15 feet. And the area of this shape here was 240 square feet. Find the area of this shape here. I'll give you a few minutes. Okay, so let's take a peek. We've got our ratio of lengths. Oops. Ratio of lengths. So, gentlemen, what's our ratio of lengths? 10 to 15, or I'm going to reduce that to 2 to 3. So to find my ratio of areas. So my ratio of areas is found by doing what? Squaring. So 2 squared is 4, 3 squared is 9. Very good. On the other side, where does the 240 go? It's from the smaller figure, so it does go on top. Cross multiply and divide. 9 times 240 divided by 4 is 560. Is that correct? 540. You're correct. So that's 540 square feet. What do you think? Okay, just break time. Let's take a quick break and we'll come back and we'll keep going. So the next step of this is what happens if we have a three-dimensional object. Let's take something like this. A little bit weird shape again. Oh, come on now. So let's take an object like this and we're going to enlarge a three-dimensional object now. And so let's say this dimension here goes from being 12 feet up to 16 feet. And the surface area of this, oh, let's say that it was 1,680 square feet of surface area. What's the surface area of this larger one going to be? Well, we're starting out the same way again. We have a ratio of lengths. What's our ratio of lengths, gentlemen? We have a 12 to 16. Now, again, to make it a little easier on myself, I'm going to reduce that. Both of those can be divided by what? 4, which gives us a 3 to 4 ratio. Now then, to work with a ratio of his surface area, is that really just an area? Yes, it is, actually. It's going to have the same relationship as any other area. So we're going to take that 3/4 and we're going to square it. What's 3 squared? 9. And what's 4 squared? 16 is correct. So that's going to be a 9 to 16 ratio. Over here, where's the 1680 go? Yes, the 12 is the smaller number, so the 1680 goes on top of the smaller number. So then we will cross multiply and divide. 16 times 1680 divided by 9 is what, 945? No, 9,450? Let me double check that. Something's off there. Well, it's three-dimensional, but it's 29, holy crap, 2986.67. That is going to be square feet. Shouldn't we cube it? Well, this is still just squared feet, even though it's three-dimensional. If we hit volume, volume's a cubic dimension. Yes, then we have to cube it. That's actually our next step. Let's take the same figure here. These same figures, and instead of comparing areas, let's compare volumes. Let's say that the volume of this small one is, oh, let's see here. Let's go 600 and, wow, the old mind is not working today. 72 cubic feet. Let's find the volume of this one. Well, we have that ratio of areas still that's 3 to 4. To find the ratio of volumes, you are absolutely correct. We would cube it. 3 to the third power is 27. 4 to the third power is 64. Now we have the 672 square feet from the smaller one. We will cross multiply and divide again. 64 times 672 divided by 27. So 1592.89 square feet. What do you think? That's not square feet, that should be cubic feet, by the way. That's volume. Cubic feet. Yeah. So anyway, let's take a look at a special little problem here. So we've got two figures here. Want to compare the heights? Want to compare the surface areas? And I'm going to want to compare the volume. Let's say that I tell you that the ratio, the surface areas for each, let's give you the surface areas for each here first. Let's say that this one is 480 square inches of surface area. This one is 1,080 square inches of surface area. This one has a height of 27 inches. This one has a height of, or volumes, or sorry, let's go over here. This one has a volume of 960 inches cubed. How to find the height and the volume, missing volume for those figures? We use ratios, and the only thing that we have both numbers for is the surface areas. That is a ratio of areas. So I have that 480 over 1,080. Can that be reduced? I sure hope so. They both end in 0, so they can both definitely be divided by 10. 480 divided by 10 is 48. 1,080 divided by 10 is 108. They can still both be divided by, let's try 4. 48 divided by 4 is 12. 108 divided by 4 is 27. Can they still be divided? They can both be divided by 3. Gives us a 4/9 ratio, correct? That's our ratio of areas. Let's find the ratio of lengths next from that. How would I find the ratio of lengths from that? A ratio of areas? If I had the ratio of lengths, how would I get to the ratio of areas? I would square it. So going the other way, I square root. Exactly. Just like doing a squared, when I do a square root, I can do the numerator and denominator separately. What's the square root of 4? 2. And what's the square root of 9? 3. So our ratio of lengths is going to be 2 to 3. Where's the 27 inches go? It is from the larger figure. It goes on bottom. We will cross multiply and divide, giving us 18. So this height is 18 inches. Make sense? Any questions on how I got the 18 inches? Okay. Now I still have that ratio of lengths of 2 to 3. I need to look at the ratio of volumes. What am I going to do that ratio of lengths of 2 to 3 in order to turn it into volumes? Cube it. Good. 2 to the power 3 is 8. How about 3 to the power 3? 27. Where's the 960 going to go? Top. That is from the smaller figure. So we shall cross multiply and divide. 27 times 960 divided by 8. 3240 gives us a volume. 3,240 inches cubed. What do you think? Not terrible? Better than a sharp stick in the eye? Okay. I'm going to shift gears just a little bit. There's a worksheet I'm going to give you on those here in a little bit. But I also want to go over, you've got that packet that we did last week that had all the measurements on the front, adding and subtracting, multiplying, dividing measurements. Yes, we're going to be doing a lot of work out of that over the next couple weeks, so make sure you don't lose that one. We're going to flip to the back page of that packet, and we're going to do ratios with measurements. But we're actually not ratios, proportions with measurements. They're not going to be ratios, they're actually going to be rates. because the units are going to be different. We might have something like 4 quarts is equivalent to 7 pounds. And we want to know 2 pints would be how many ounces? Well, to do these, this is a rate because the unit on top and the unit on bottom are different. A ratio, remember, has the same unit so that they cancel out. But even with a rate, the units on the left side have to be the same as the units on the right side. And here they are different, so we're going to have to do some conversions. I either have to turn this into quarts or this into pints. I usually convert to the smaller unit because then you don't have to deal with ugly decimals or fractions. 4 quarts is how many pints? 8. There are 2 pints in a quart, so 4 times 2 is 8 pints. I also have to convert the pounds and ounces. 7 pounds is how many ounces? Well, 7 times 16 is 112 ounces. So now, once again, we will cross multiply and divide. 112 times 2 divided by 8 is 28. Does that look right? Ounces. Perfect. Well, what if I have that 2 pounds will dissolve in 9 gallons? And I want to know how many ounces will dissolve into 3 quarts. I'm going to have you guys try this one in your notes, see what you come up with. Okay, so we've got to get our common units here. Again, I'm going to convert to the smaller unit. So 2 pounds becomes how many ounces? 32, very good, so times 16. 9 gallons becomes how many quarts? 36. Now, I actually could reduce these if I wanted to. Both of those would divide by 4. I could end up getting an 8 to 9 ratio. But let's just do 32 times 3 is 96. Divided by 36 is 2 2/3 is correct. Let's say we have a loading of 7 ounces over 12 square inches. I want to know how many pounds would that be over 5 square feet. So here we're going to have to convert. Now the ounces to feet isn't going to work real well. What we're going to do is we're actually going to find our answer in ounces, ounces to pounds. We're going to find our answer in ounces and convert it to pounds later for now. Down here, though, we can convert my 5 square feet into square inches. What's my conversion? Multiply by 144. So that's going to be 720, correct? So now we'll cross multiply and divide. 7 times 720 divided by 12, which is going to give us, what, 42 ounces? So now we've got to convert that into pounds. Divided by 16. 16 goes into there twice with 10 left over. So that's 2 10/16, or 2 5/8 pounds. What do you think? Actually, 144 square inches is 1 square foot. So this was times 144 here. You get 0.083333333333. That doesn't work. Here's one for you guys to try in your notes. Let's say that we are looking at having a And well, let's do this. 18 pounds in 7 cubic feet. Want to know how many ounces that would be in 15 cubic inches. I'm going to give you a minute to do that. Okay, so let's convert the 18 pounds. 18 pounds becomes how many ounces? What's that? 288? Okay, yes. 7 cubic feet becomes how many cubic inches? 12,096. Yes, it is, of course, 1,728 times 7. So then we'll cross multiply and divide. 288 times 15 divided by the answer is 0.357. No, the 18 is gone. Those are gone. No. Let's try another one similar to that then. Let's say you were going to do an additive, and the additive calls for 1 cup to be added to every 50 cubic inches. I want to know how many gallons to be added to a tank that is 200 cubic feet. Give that one a shot. See how you do. So now here, we're going to have to convert to gallons later, but for now, we're going to leave it as 1 cup. I'm going to turn this 200 cubic feet into cubic inches. 200 cubic feet times 17 is 28 is 34,000, actually 345,600 cubic inches. So we're going to do 1 cup times that divided by the 50 for the cubic inches gives us 6,912. Now this is still in cups. So we have to divide by 16. 432 gallons that we came up with? Perfect. Okay, also, so what I'm going to have you do is I'm going to give you a new worksheet, which is going to be on these ratios of areas and volumes. And then in that packet, it's going to be that last page of the packet where it has those ratios with the measurements in them. Now, I want to warn you a little bit in this worksheet with the areas and volumes ratios. Sometimes it's tricky to figure out whether it's a ratio of area or a ratio of volumes. It might be talking about a volume, but it's still an area. For example, let's say that you have an 8-inch pipe can discharge 300 gallons per minute. How much could a 10-inch pipe discharge? Well, we're looking at this, and it appears to be a volume because, well, gallons is a capacity, which is related to volume. But it's not. We're changing the diameter of the pipe, going from 8 inches up to 10 inches. We're not changing a volume. To change a volume, we'd have to actually change the flow rate of the water coming through it. The water would actually have to come through faster velocity as well. We're changing a length and a width, or a width and a height, however you want to look at it, but we're not changing a depth. So we don't have that third dimension to be volumes. So this is really a ratio of areas. So we have that ratio of lengths of 8 to 10. which I'm going to reduce to 4 to 5. I'm going to square that to get 16 to 25. And that's going to be my ratio of area, cross-sectional area, which is going to be the discharge ratio. 300 goes with the smaller one, so it's going to be 25 times 300 divided by the 16, which will give me, now that didn't work out right, 25 times 300 divided by 16, which will give me 468.75. So the 10-inch pipe can discharge 468.75 gallons per minute, as opposed to the little one. Okay, I'll get you those worksheets right now.